Yes, recording has started. So now let me share the screen for that. Fine. So now we have seen an example of estimation method. We have also seen an example of how to calculate the efficiency. Now we will talk about method of moments. Okay. So this will be class 4, Econometrics 1. So now we'll talk about method of moments. So method of moments is also an estimation technique whereby we equate the population moments. So what are the moments of the any distribution of population? Mean, variance, then mode. So these are the moments of any distribution. So if we equate the, so under this method of moments estimation method, we equate the population moments and the sample moments. To get required estimates of population moments. Okay. Now, Obhigyan, can you see me properly?
Yes, sir.
So now let us consider binomial distribution. So in case of binomial distribution, there is a population parameter which is known as P. Now, binomial distribution, there are two things that are of consequence. One is the population parameter P and the size of the sample in the binomial distribution, that is N. Okay. So now let us consider that we know the sample mean, which is one of the moments of this distribution, sample mean, which is X bar. Okay. Fine. Okay. So now, so this is a sample mean. Now what is the population mean? Population mean will be equal to N of P, where P is a population parameter. So now we will be equating sample mean and population mean. X bar equal to N and P. So now if we know the sample mean, if sample mean and N are known, then we can estimate the population parameter P. Now let us consider a situation. So this is one situation. So this is situation 1. Now situation 2. Both N and P are unknown. Okay. So both P and N are unknown. Now population mean, okay, sorry, the sample mean as well as the sample variance A square are known. Okay. So now we have two parameters. So now apart from P, we will consider one more parameter, which is Q. Now Q is nothing but 1 minus P in binomial distribution. So now we know what is sample mean. Sample mean is equal to X bar sample variance equal to S square. Now we know what is population mean. Population mean is equal to N of P, and we also know what is population A variance. So population variance will be equal to NPQ, which is nothing but NP into 1 minus P. So this is nothing but NP minus NP square. Okay. So this is what we can write this as. This we can write as NP minus P square. So now we can equate the sample mean X bar equal to population mean, which is NP. So this forms one equation. Then we can equate the sample variance S square equal to population variance, which is NP minus NP square. So now we have got two equations in two unknowns. What is the one unknown? One unknown is NP, the other unknown is, one unknown is N, the other unknown is P. So if we know the sample mean and sample variance, and if both N and P are unknown, then using the expression for population mean, population variance, we can equate them to sample mean and sample variance, and then we can estimate the values of N and P. Okay. So next we come to sampling distribution of a statistic. So let's say what is the statistic? The statistic is mean. Okay. Now there is a population of size capital N. Now you draw a random sample of size N without replacement. Okay. Then what are the possible number of random samples? Possible number of ways a random sample of size N can be drawn from a population of size N equal to what? N Cn. Okay. So let this number be equal to K. So that means there are K possible random samples. Okay. There are K possible random samples. Now corresponding to each random sample, corresponding to each random sample, the estimated T, which is the sample mean. So this is estimated T is for the sample mean, gives the sample mean. Okay. So now there are k sample means because there are k random samples. That is T1, T2 to Tk. Now this number, they form a sampling distribution of the of the statistic. So they are now forming a sampling distribution. Okay, sampling distribution of the statistic, which is nothing but a sample mean. Okay. Now we will find the mean of this sampling distribution of the statistic. Okay. So the mean will be given by what? Expected value of t. So this will be summed over all the values of t. 1 by k summation ti I equal to 1 to k, and the variance of the sampling distribution of the test statistic, which is E of t. So this will be nothing but what? 1 by k. Okay, 1 by k summation what? Ti minus et whole square I equal to 1 to k. Okay, so this we can write as k summation t minus t bar whole square. Okay, so these are the 2a. Now what is the standard error of this sampling distribution? Standard error will be nothing but root over variance, square root of the variance, which is again what? Which is again 1 by k t minus t bar whole square. Okay. Now, when we calculate these two parameters of the sampling distribution, that is the sample mean of the sampling distribution of the statistic and the variance of the sampling distribution of the statistic, we can use those two values to find a lot of things. So what is there? So we like to find the precision of the test statistic which has been estimated. So precision of t will be given as nothing but 1 by standard error. So this is nothing but 1 by root over k summation t minus t bar whole square. So here we are using the 2a. First t bar we have to compute, and then after computing t bar we are calculating the variance, and from variance we get the standard error. So these two values helps us to estimate the precision of the t, that is how accurate, so measure of accuracy. Okay. Next, we would like to test the significance of the difference between the sample mean of the sampling distribution and the population mean. So whether the difference between the two is due to fluctuations in the sample, or there is a significant difference or not. Okay. We can use it further for what? We can use it further for to test the significance of the difference. between two independent estimates of the statistic. That is, we are using two different estimators, and then we are trying to find there's a significance of the difference between them. Okay. We also use this to estimate make point estimation of the population parameters. Population parameters. Okay, just a minute. Okay, so to make point estimation of the population parameters, then also to obtain interval estimates of the population parameters. Okay, so to obtain the estimates of the interval estimates of the population parameters, now you would like to find the sampling distribution of the mean. Okay, so we have already discussed, so sampling distribution of the mean. So now we are discussing, so this was a particular test statistic. Now we would like to discuss about a particular test statistic. So this was a general discussion about a test statistic. Now we would like to discuss about a particular test statistic, which is the mean. So sampling distribution of mean. Okay. So what is the variance of the sampling distribution of mean? So variance of x. So if you're drawing a random sample, so if you're drawing a random sample without replacement. So what do you mean by drawing a random sample without replacement? Vigyan? What do you mean by that? Drawing a random sample without replacement, what do you mean by that? Vigyan? What do you mean by that? Drawing a random sample without replacement? Vigyan? Are you present? So what do you mean by drawing a random sample without replacement? What do you mean by that? So here we are drawing a random sample without replacement of size n, from a population of capital size n, from a population size capital N. So in that case, the variance of the sample mean, variance of the sampling distribution of mean will be given by this sigma square by n into n minus capital N minus small n, capital N minus 1, where small n is the sample size Okay, and capital N is the population size. Now, if capital N is very large, that is N tends to infinity, then we can write N minus 1 as almost similar to capital N. Okay, so in that situation, we can write the variance of x bar. We can write the variance of x bar as sigma square by small n into capital N minus n by n. So we can write the term in the bracket as follows: 1 minus small n by capital N. Now, if n is very small relative to capital N, then capital N, small n by capital N tends to 0 as n tends to infinity. Okay. So in that case, we can then write variance of the sampling distribution of mean equivalent to sigma square by n. Okay, which is same as the variance of the random sample with replacement. Okay, variance of the sampling distribution of mean where the random sample is drawn with replacement. Fine. Now, as n rises, this variance of x will also keep on falling. So, when n becomes very large, then variance of x will tend towards, x bar will tend towards 0. That means in such a situation, the sample estimate of the mean sample estimate of the mean will be approximating closely the estimate of the population mean. Okay, so the estimate sample mean, so the estimated sample mean will then closely approximate the population mean when n becomes very large. That means when the size of the random sample becomes very large. Now, okay, so now next we come to something which is known as the central limit theorem. So what do the central limit theorem stand for? What does the central limit theorem stand for? It says that if x1, x2, xn is a random sample of size n, then this random sample of size n, then the sample mean, that is x bar, okay, then the sample mean x bar will be normally distributed. So if we draw a random sample of size n, then the sample mean x bar, which is the estimate of the from each of the samples, will be normally distributed. That means if you are estimating k sample means, then they will be normally distributed as n x bar sigma square by n. Okay, where x bar is the sample mean and sigma square by n is the sample variance. Okay, so it is not necessary that this random sample has to be drawn from a normal population or the so it is not necessary that it has to be drawn from a normal population. So even then, when it is not drawn from a normal population, still then the sample mean will be normally distributed as n x bar sigma square by n, provided n is very large. That means n tends to infinity when the population is not a normal population. Normal one. So in that case, this sample mean x bar will be asymptotically normal, asymptotically normally distributed, as in x bar sigma square by n. Okay. So I have to make a small correction here. So I've seen that if x bar, x1, x2, xn is a random sample of size n, then the sample mean will be normally distributed as. So instead of x bar, we will be writing this as the mu. Okay. So where mu is the population mean. Okay. And sigma square n is the population. So we are considering now this as the population variance. Similarly here also. Asymptotically normally distributed. Okay. So this is the general idea of the central limit theorem. So what is the actual theorem? So actual theorem is this: if x1, x2 to xn are random variables from any distribution, then summation of all these values of these random variables, that is summation equal to x1 plus x2 till xn. So this will be asymptotically normal as n tends to infinity. This means as the number of random variables becomes infinitely large from any distribution, then the summation of these random variables will be asymptotically normal as n tends to infinity. Okay. So that means when we are considering a standardized random variable, so let us consider standardized random variable. So where xi is the random variable and the standardized form is x minus mu by sigma square by n, root over sigma square by n. Okay. So root over sigma square by n. So whenever the central limit theorem stands, so in that case, this standardized random variable will also be asymptotically normally distributed. So this is standardized random variable. Okay. So will be asymptotically normally distributed as n with mean of 0 and a variance of 1. Population mean of 0 and a population variance of 1. Okay. Fine. Now, let us get to certain examples. So now let us consider this example 16.2. So what is the example? So there is a population of 5 numbers. So what are those numbers? 2, 3, 6, 8, 11. Okay. So they can be, so out of these 5 numbers you can draw 2 numbers. So you can draw a random sample of 2 numbers with replacement. So we can draw a random sample of 2 numbers with replacement. So the possible number of random samples. So we can draw the first number in 5 different ways. Okay. Then we can also draw the second number in 5 different ways. So the total number of possible number of random samples will be 25. Now let us see what are those what are all those random samples. So first we have to draw the random sample, then we'll have to calculate the sample mean, and then we'll have to calculate the standard error of that sample mean. Okay. So first, what are the possible samples? So this is the sample number. Okay. This is the sample being drawn and the corresponding sample mean. So there will be 25 samples. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So what are the possible samples? We already know what are those numbers: 2, 3, 6, 8, 11. So first we'll have to do 2, 3. Okay. Then 2, 6. Okay. Then 2, 8. Okay. 2, 3, 2, 6. Just a minute. Just a minute. So 2, 2, 2, 3, 2, 6, 2, 11. Next, 3, 2, 3, 3, 3, 6, 3, 8. So these are the first 9A. Now we'll have to calculate the sample mean. So this is nothing but 2. This is 2.5. This is 4. This is 5. This is 5.5. This is 2.5. This is 3. This is 4.5. Okay, and the last one was 5.5. Sorry, 211. This is not 5.5. This will be 6.5. Just a minute. This is 6.5. 211. So 2, 2, 2, 2, 3, 2.5, 4, 5, 6.5, 2.5, 3, 4.5. So now we'll have to find the next 16 samples. So we are into page 6. So this was page 6. So we will now be into page 7. Okay. So 10, 11, 12, 13, 14, 15. So this will be 3, 11, 10, 2, 3, 6. 6, 2, 6, 3, 6, 6, 6, 8, 6, 11. So the sample mean 7, 4, 4.5, 6, 7, 8.5. Next 5, 16, 17, 18, 19, 20. So now 2, 3, 6, 8. So this will be 8, 2, 8, 3, 8, 6, 8, 8, 8, 11. So this is nothing but 8 to that means 5, 5.5, 7, 8, 9.5. So the last 5 random samples, that is 21, 22, 23, 24, 25. So now this will be 11, 2, 11, 3, 11, 6, 11, 8, 11, 11. So this is nothing but 6.5 sample mean, 7, 8.5, 9.5. This is 11. So these are the sample means. So now you will have to calculate the, so now this is a sampling distribution of the mean. Okay. So what is sampling distribution of the mean? This 25 means drawn from 25 samples. So now you'll have to take the mean of this sample means, which will give me the mean of the sampling distribution of the test statistic, which is nothing but the mean. Okay. So now I'm just shortening this calculation. So when I shorten this calculation, what I get the sampling distribution of the mean. Okay. So if I get the sampling distribution of the mean, what is the sampling distribution of the mean? Expected value of x bar, which is nothing but I add up all the values of the sample means, which gives me the summation xi bar. What are the total size of number of samples? That is 25. So this was nothing, 150, you have to check it, and this is 25. So this is the mean of the sampling distribution, the test statistic. And what is the test statistic? We're trying to find the mean. Okay. So the test statistic is the mean, and the sampling distribution of the test statistic, mean of the sampling distribution of the test statistic is 6. Now we'll have to find the variance of this sampling distribution of the test statistic. That is variance of x bar. So same formula, that is 1 by n summation, that is xi. So this is xi bar minus x bar square 1 to 25. So this is 1 by 25. So I have to now find xi bar minus x bar square 1 to 25. So again, I'm shortening it. I'm not getting into the details. You have to find it yourself. So here what I'm getting is this. So this is giving me summation equal to what? So this summation is nothing but equal to 135. Okay. So 135 by 25 is equal to what? 5.4. Fine. So these are the mean of the sampling distribution of the test statistic and variance of the sampling distribution test statistic. Now, what is the population mean? Population mean is nothing but we calculate the simple mean, that is 2 plus 3 plus 6 plus 8 plus 11 divided by 5. So 2 plus 3 5, 5 plus 6 11, 11 plus 8 19, 19 plus 11 30. So 30 by 5 equal to 6. That means the population mean is exactly equal to the this mean of the sampling distribution. That means the test statistic, that is a sample mean, gives an unbiased estimate of the population mean. Okay. Now, what is the population variance? Population variance will be nothing but number of observation 1 by 5. So this is 2 minus 6 whole square plus 3 minus 6 whole square plus 6 minus 6 whole square plus 8 minus 6 whole square plus 11 minus 6 whole square. Okay. So this is 1 by 5. Within bracket we have minus 4 whole square plus minus 3 whole square plus 0 square plus 2 square plus 5 square. Okay. So 1 by 5. So this is nothing but 16 plus 9 plus 0 plus 4 plus 25. So this is what now what? This is nothing but 54. 16 plus 9 25, 29 plus 25 54, 54 by 5 equal to what? This is equal to 10.8. Okay, this is equal to 10.8. So which is nothing but your population variance sigma square. Now we'll have to find the so now we'll have to find, so we have a population mean mu is equal to 6, which is equal to the expected value of this sampling distribution of the text statistic. Now we have to calculate, so what is the population variance? Population variance sigma square is equal to 10.8, but this is not equal to the population variance sample variance of the sampling distribution of test statistic. But we know what? We know that how can you sampling distribution of the test statistic, this variance of the sampling distribution is nothing but a square equal to sigma square by n. So what is sigma square? Sigma square is nothing but 10.8. And what is the n? N is nothing but the size of the sample, which is 2, so equal to 5.4. So this is now equal to what? This is now equal to this variance of the sampling distribution of the test statistic, which is the mean. Okay. So now we have to find the standard error. So how do you find the standard error? Standard error is nothing but sigma square by n. So what is sigma square by n? It is nothing but summation over as a root over 5.4. And what is root over 5.4? It is 2.32. So the standard error of the sampling distribution test statistic is 2.32. Okay. So we stop here today. Okay. So thank you and see you in the next class.